Right now, as I'm speaking to you, artificial intelligence is accidentally making our programming languages less diverse, not more. Every time a developer asks ChatGPT to write code, every time GitHub Copilot suggests a function, it's more likely to spit out Python, Java, or C++. Why? Because that's what it learned from. And here's the kicker. That creates more Python and Java code, which trains the next generation of AI models, which suggests even more Python and Java. We've created a feedback loop that's cementing the dominance of languages that were already winning 30 years ago. Welcome to Mindcast, where we explore the hidden forces shaping our digital world. I'm your host, Will, and today we're diving deep into something called the Ergonomics of Economics, a fascinating academic paper that challenges everything you think you know about why some programming languages succeed while others fail. Now, before you click away thinking this is going to be dry computer science theory, stick with me, because this research reveals something profound about how all technological choices get made in our world. Whether you're choosing a smartphone, a car, or yes, a programming language, the forces at work are the same, and they're not what you'd expect. The paper we're exploring today takes on Kevlin Henney, a respected voice in the programming world who argues that languages evolve based on theoretical elegance, particularly functional programming concepts like immutability and composition. Henney characterizes programming languages as a halfway house between the metal and the mind, bridging the rigid world of circuits with the fluid, chaotic world of human thought. And he's not wrong about the history. Most of what we call innovation in modern programming is actually recycling ideas from the 1960s and 70s. But here's where our researcher challenges that narrative. If theoretical purity and expressive power were really the main drivers of language adoption, languages like Lisp or Haskell would have conquered the industry 40 years ago. They didn't. Instead, what we see dominating the landscape in 2025 are languages that solve very practical, very economic problems. Languages chosen not because they're theoretically beautiful, but because they make business sense. Over the next 20 minutes, I'm going to walk you through 3 key insights from this research that completely reframe how we think about technological adoption. First, we'll explore the archaeology of programming, how innovation is really just excavation of old ideas, and why that matters. Second, we'll dive into what I call the Google scale problem, how Go was invented to solve build times, not paradigms. And third, we'll unpack that AI paradox I opened with. By the end, you'll have 3 concrete insights about what really drives technological success in 2025, insights that apply far beyond just programming. Let's get started. Let me start with a story that reveals the first key insight. It's 2020. And the C++ Standards Committee is celebrating. They've just added coroutines to C++20, this revolutionary new feature that will transform how we write concurrent code. Except, coroutines were invented in 1958. Pattern matching, another cutting-edge feature being added to various languages, that's from the 1970s. Lambda functions, which everyone got excited about when they came to Java, lambda calculus predates the digital computer itself. This is what our researcher calls the archaeology of ideas. The history of programming languages isn't really about innovation, it's about excavation. We keep digging up the same concepts, dusting them off, and presenting them as breakthroughs. Now, why does this happen? Here's where it gets interesting. These ideas aren't succeeding now because we suddenly discovered how brilliant they were. They're succeeding because the context has finally changed enough to make them viable. Take immutability, the idea that once you create a piece of data, you never change it. Functional programming advocates have been preaching this for decades, but it's not succeeding now because developers suddenly embraced mathematical purity. It's succeeding because we all have multi-core processors in our laptops,
and immutable data is much safer when you're running code in parallel. The hardware reality changed, so the software idea became economically viable. This reveals something profound about technological adoption in general. New ideas don't usually win on their merits alone. They win when the economic and practical context shifts to make them the obviously better choice. The iPhone wasn't successful because Apple invented the smartphone. They didn't. It was successful because battery technology, processor efficiency, and network infrastructure had finally reached the point where a pocket computer made economic sense for millions of people. But here's the twist. Despite all this recycling of old ideas, the actual rate of language evolution and adoption has slowed dramatically. The languages dominating the landscape in 2025, Python, Java, C++, JavaScript, are largely the same titans that ruled the 1990s. Why? Our researcher calls this the incumbent effect. The gravitational mass of existing code in ecosystems creates a barrier that mere innovation cannot overcome. Think about it this way. Every line of code ever written creates a kind of debt. Not technical debt, economic debt. Someone has to maintain it, understand it, modify it. The cost of rewriting software is astronomical. As systems age, they accrue what the paper calls accidental complexity. All the friction from tooling, interfaces, and legacy decisions that have nothing to do with the actual problem you're trying to solve. This is why languages like C++ continue to thrive despite being notorious for what programmers call foot guns, features that make it easy to shoot yourself in the foot. It's not that C++ is great, it's that the sprawling metropolis of C++ libraries, frameworks, and dependency chains is so massive that replacing it would cause more problems than it would solve. The halfway house between metal and mind has become a sprawling city that's too expensive to demolish. This brings us to our second key insight, which I call the Google scale problem. And this is where we see economic forces truly driving language design. Picture this. It's the mid-2000s at Google. They're building systems that handle billions of web searches. Their engineers are brilliant. Their hardware is cutting edge. But they have one massive productivity-killing problem. Their C++ code takes hours to compile. Now, think about what this means from a developer's perspective. You make a small change to your code. You hit compile. You wait 45 minutes to see if it works. During those 45 minutes, you lose what psychologists call flow state, that deep focus where you're most productive. You start checking email, browsing the web, getting distracted. Even when the build finishes, it takes time to get back into the zone. This wasn't a paradigm problem. This was an economic disaster. So Google invented Go, not to advance the theoretical state of programming, not to embrace functional programming or achieve paradigmatic purity, to solve build times. Go was designed from day one with fast compilation as a fundamental requirement. They eliminated features that slow down parsing, like complex preprocessors and circular dependencies. They enforced a strict dependency model that makes compilation predictable and fast. The result? Go compiles to native code almost instantaneously. This created something magical, a development cycle that feels like working in Python but gives you the performance of C++. And here's the kicker. Go also solved the training problem and the code review problem through what they call boring simplicity. By deliberately omitting features like inheritance and method overloading, Go forces a standardized coding style that any developer can read and understand quickly. This reveals our second major insight. Successful technologies solve concrete, measurable pain points, not abstract philosophical problems. Go didn't succeed because it was theoretically elegant. It succeeded because it reduced compilation time from hours to seconds and onboarding time from weeks to days. When you're managing a 1,000-person engineering team, those metrics translate directly to millions of dollars in productivity gains. But let's dig deeper into something that I find absolutely fascinating: the speed versus velocity paradox. This perfectly illustrates why economic forces trump theoretical ones. On one hand, you have C, incredibly fast at execution, close to the hardware. In computational loops, C can be orders of magnitude faster than interpreted languages. For embedded systems, operating system kernels, high-frequency trading, C is non-negotiable because latency is literally the product. On the other hand, you have Python, notoriously slow at execution. We're talking 50 to 100 times slower than C for CPU-intensive tasks. But here's the thing: Python dominates data science and AI development. Why? Because for most applications, time to market is the critical metric, not execution speed. The research shows that Python can reduce development time by a factor of 5 to 10 compared to lower-level languages.
But here's the really clever part. Python rarely runs pure Python for heavy computational work. Libraries like NumPy and PyTorch are actually wrappers around highly optimized C and C++ cores. So, Python allows developers to orchestrate C speed performance with Python speed development. It's the best of both worlds. You get the execution speed where it matters and development velocity everywhere else.
Now this brings us to our third and most mind-bending insight, the AI feedback loop paradox I opened with. And this is where things get really interesting for the future. Large language models like ChatGPT and GitHub Copilot are trained on vast repositories of public code, primarily from GitHub. Because the training data is heavily biased toward the most popular languages, AI coding assistants are most proficient in Python, JavaScript, Java, and C++. Here's the self-reinforcing cycle. Developers use AI tools to generate code. AI suggests Python or Java because that's what it knows best. More Python and Java code gets written and pushed to repositories. Future AI models are trained on this expanded dataset, making them even better at Python and Java and even worse at newer languages. It's like a technological version of the rich getting richer. This means that new languages like Zig or Odin face a double disadvantage. They not only lack the ecosystem of libraries and frameworks that established languages have, but they also lack the AI fluency that modern developers increasingly rely on. A new language today must appeal not just to human developers, but to the AI assistants those humans use. That's a completely new constraint in the history of programming. Now, there's one more economic force that's reshaping the entire landscape, and that's safety as a business requirement. Microsoft and Google have both reported that approximately 70% of their critical security vulnerabilities are memory safety issues, buffer overflows, use after free errors, and other problems inherent to languages like C and C++. When security breaches can cost hundreds of millions of dollars, memory safety stops being a theoretical nicety and becomes a fundamental business requirement. This is driving the rise of languages like Rust, which promises C-level performance with memory safety through something called the borrow checker. Now, Rust has a notoriously steep learning curve. It might take months for a team to become fluent, but here's the economic trade-off. That upfront training cost pays dividends in reduced debugging time and eliminated security vulnerabilities. It's a classic example of shifting costs from runtime to development time, from operations to engineering. So, what does all this mean for how we think about technological adoption in 2026? Let me give you 3 concrete takeaways that apply far beyond programming languages. First, innovation is often just the right old idea meeting the right new context. Don't dismiss something because it's been tried before. Ask whether the economic or technical context has shifted enough to make it viable now. Second, practical constraints often matter more than theoretical advantages. The technologies that win are rarely the most elegant or pure. They're the ones that solve the most expensive, most painful problems. Go didn't succeed because it was paradigmatically superior to C++. It succeeded because it eliminated 45-minute build times. When you're evaluating any technology, look for the concrete pain points it addresses, not just its feature list.
Third, in an AI-augmented world, technologies need to be learnable by machines, not just humans. This is probably the most profound insight for the future. As AI becomes more integrated into how we work, technologies that play well with AI systems will have massive advantages. The feedback loops we're seeing in programming languages are just the beginning. This same dynamic will play out in design tools, writing platforms, data analysis software, anywhere AI assistants are becoming integral to the workflow.
Looking ahead, the languages that will dominate the next decade won't necessarily be the most theoretically pure or paradigmatically advanced. They'll be the ones that best balance what a researcher calls the books of software engineering. They'll reduce latency in build times, in onboarding, in the feedback loop between writing and testing code. They'll enforce safety without imposing excessive cognitive load, and they'll prioritize local reasoning, the ability to understand a piece of code without needing to understand the entire system. And critically, they'll bridge the gap with existing systems. The sheer weight of legacy C++ code in financial systems, browsers, and games means that completely new languages need interoperability strategies. This is why we're seeing languages like Carbon from Google, designed specifically for bidirectional interoperability with C++. It's not trying to replace C++ ideologically, it's trying to migrate from it economically. So here's my challenge for you as we wrap up. The next time you encounter a technological choice, whether it's a programming language, a productivity app, a smartphone, or any other tool, don't just ask whether it's innovative or theoretically superior. Ask these 3 questions. What concrete, expensive problem does this solve? What practical constraints does it address that others ignore? And in our AI-integrated world, how well does it play with the intelligent systems we're increasingly relying on? The ergonomics of economics aren't just reshaping programming languages. They're the hidden force behind every technological choice we make. Understanding them gives you a superpower for predicting which technologies will thrive and which will fade into obscurity. Because in the end, the perfect technology isn't the one with the purest paradigm. It's the one that best balances the books of human effort, economic reality, and practical constraints. Thanks for joining me on Mindcast. I'm Will, and if this kind of deep dive into the hidden forces shaping our technological world resonates with you, subscribe and share this episode with someone who loves understanding the why behind the what. Until next time, keep questioning the conventional wisdom, and remember, the most profound innovations often look like the most practical solutions to expensive problems.